Welcome to the AI Research Roundup. I'm Alex. Today, May 10th, 2025, we're looking at an ICLR conference paper, Problem Parameter-Free Federated Learning, published a little over 3.5 months ago. It tackles a key challenge in federated learning, or FLORIDA, a method for training AI models across many devices without sharing their private data. Current FLORIDA often requires meticulous tuning of hyperparameters. These are settings like learning rates that control the learning process. This paper proposes a new algorithm that avoids this complex, problem-specific tuning, performing robustly even with significant data heterogeneity, which is when data varies greatly between devices. Alright, so this table on page 8 really highlights the core advantages. It compares their proposed methods, PAdaMFed, and its enhanced version, PAdaMFed VR, which uses variance reduction, a technique to speed up learning, against other federated learning algorithms. Crucially, their methods don't need additional assumptions like some others, nor do they rely on step size related problem parameters, those tricky data-specific settings. And importantly, for communication complexity, which is how much data needs to be exchanged, they achieve excellent efficiency, with PAdaMFed VR matching the best-known rates. This practical benefit is a big step forward. Building on that efficiency, these plots from page 9 visually demonstrate the robustness to learning rates. We're looking at test accuracy, essentially how well the model performs, against different learning rates, which are settings that control learning speed, on the EMNIST dataset. Plot A is for IID data, that's independent and identically distributed data, so fairly uniform data across devices. Plot B is for non-IID data, where data varies more. Notice PAdaMFed, the red line, stays accurate across a wider range of these learning rates, especially in the non-IID case, really underscoring its stability without needing careful tuning. Okay, so these next plots, also from page 9, visualize the learning progress. We're looking at test accuracy on the vertical axis, plotted against the number of communication rounds, which is how many times the devices coordinate with the central server on the horizontal axis. Again, plot A is for IID data and B for non-IID data. Notice how PAdaMFed, the red line, and particularly PAdaMFed VR, the purple line, climb to higher accuracy faster. This really demonstrates their superior convergence speed, meaning they learn effectively in fewer rounds and achieve better overall performance. Continuing with that theme of performance, these next plots, this time from page 27 and using the CIFAR10 dataset, another common image recognition benchmark, further illustrate these trends. We're again looking at test accuracy on the vertical axis against communication rounds, with plot A for IID data and plot B for non-IID data. PAdaMFed, the red line, is compared against several established federated learning methods like FedAVG and Scaffold, which is a framework that aims to correct for differences in client data. Notice PAdaMFed consistently achieves high accuracy faster, particularly in the non-IID setting, reinforcing its efficiency and robustness. So, having seen how PAdaMFed stacks up against other methods, the authors also performed an ablation study. This is where they essentially take apart their own algorithm to see which individual components contribute most to its success. These plots from page 28 show this on the CIFAR10 dataset, with plot A for IID data and plot B for non-IID data. PAdaMFed, the red line, combines gradient normalization, a technique for adaptively adjusting learning steps, and client-side momentum, which helps with stability and speeds up learning. It clearly outperforms using either component alone, demonstrating their combined strength. Okay, so after seeing how the components of PAdaMFed contribute, these final plots from page 28 shift back to comparing the full PAdaMFed algorithm against other established methods. We're looking at the gradient norm. This is essentially a measure of how much the model's predictions would change with tiny adjustments to its settings. A smaller gradient norm means the model is more stable and closer to converging on the vertical axis against communication rounds on the CIFAR10 dataset. Plot A is for IID data and B for non-IID data. PAdaMFed, the red line, clearly drives this gradient norm down faster, showing it converges more quickly. So seeing that faster convergence in the gradient norm really brings us to the heart of this work. In essence, PAdaMFed and its enhanced version, PAdaMFed VR, offer a robust way to do federated learning without the usual headache of tuning lots of specific settings for each problem. They handle diverse data well and achieve impressive theoretical guarantees like better sample complexity. That's how much data they need to learn, and communication complexity, meaning less back and forth between devices. This combination of features makes them highly promising. Thanks for tuning in to the AI Research Roundup, and we'll catch you next time.